Hello and welcome everyone to MSc Software's webinar series. Today's topic is Accelerating Productivity with Nonlinear Nastran. My name is Farnaz Jadbabi and I will be the host for this webinar. Our presenter today is Hanson Chang. Hanson is a senior lead application engineer with more than 10 years of experience at MSc. At this moment, I'm going to give the presentation to Hanson and he will start. Thank you.
Hello, everyone. Welcome to the webinar. Today, I'll be giving you an overview of Nastran Nonlinear Solution 400. And I'll also provide you with several productivity tips to help you run Nastran Nonlinear more productively. What I'll do today is we'll first look into a few examples on how to identify, how to spot those nonlinearities in your structural design. We'll look at a few examples in each area, and then we'll take some time and look at an example problem together. In Solution 400, we'll identify the different nonlinearities, learn how to define them, and learn how to add them to the simulation one at a time. And along the way, you'll see me demonstrating that the transition from linear Nastran into nonlinear Nastran is fairly easy for existing Nastran users. Now first, let's take a look at just linear versus nonlinear analysis. Most real-world structures, they do exhibit some nonlinear behaviors. But as structural analysts, we've been used to doing classical solutions, hand calculations from handbooks for a long time. And these equations and formulas are based on linear assumptions. You go to your favorite handbook, Broom or Rourke, or Perry, and get the equation you need, and you solve it very quickly because we assume it's linear. And often with these linear methods, we also have built-in conservatism. It's part of the methodology to make sure our solutions are conservative. The nonlinear analysis comes in when there's significant nonlinearity present in the structure. So we'll talk about that today. If that's present, and then nonlinear analysis will be required, that will give you more accurate results. As shown in this graph below here, where the red dots are the test results of a nonlinear structure, and this is a load deflection curve. You can see the dark blue nonlinear analysis tracks the nonlinear test data pretty closely, while the linear results, in this case, is just an assumption. So nonlinear analysis does allow us to sharpen our pencil and get closer to the actual structural behavior. Let's look at some of the assumptions a lot of us have been making for a lot of years, but we never even think about it. Linear assumptions, we always assume, well, it's a single Young's modulus, so it's a linear material. Displacements are small. That's a very important linear assumption. That allows us to calculate the equivalent equilibrium equations in free body diagrams in the undeformed position because the displacements are small. We assume small strain, of course. Materials are elastic, not plastic. Load path is constant. As you load up the structure, you don't have any change in behavior in the load path inside the structure. As a result of these assumptions, now we can say displacements are proportional to loads. And out of it, we can do great things like linear superposition. We can do linear unit loads. We can interact them. We can combine them. But nonlinear analysis becomes important now. For example, if your structure now is deforming substantially, right, going from small displacement to large displacement, maybe rotating quite a bit, and now we have to do the equilibrium in the deformed position. Another example would be contact. Once you start having contact, parts are touching each other, heel toeing, and so your load path is actually changing as you apply load to the structure. So those are some of the examples where your linear assumption no longer holds, and we're going to march into nonlinear analysis. So let's look at how we approach nonlinear solutions. There are two approaches to solving nonlinear problems. One approach is implicit nonlinear. Implicit nonlinear means we do not explicitly solve the actual nonlinear equations. the dynamics equations. We take our time, we implicitly divide the load into load increments. And within each load increment, we iterate and eventually reach convergence. So that's one way of solving nonlinear problems. Showing the animation here is I have a stiffened panel being loaded in plane in compression from the left. And you can see as it's being loaded, the skin will buckle first. And then the load is carried further by the stiffener. And eventually the entire stiffener and effective skin goes into plasticity and the whole section will buckle, actually go into crippling. So that sequence of events we can capture with implicit nonlinear analysis. In Nastran, that's solution 400. There's another class of problems where it happens in a very short duration. They're dynamic, things that impact crash landing, fuel tank sloshing, burst strike, engine blade out. They've happened so fast and typically in a matter of milliseconds or maybe a fraction of a millisecond. Now, when we solve a problem like that, now we use a explicit solution. Explicit solution, we actually explicitly solve the dynamic solution with very small time steps. So for example, here I'm showing a debris breaking through a composite fuselage. Right? The animation is quite slow, but it's really happening really fast. It's an impact problem. So we solve explicit nonlinear analysis in Nastran with solution 700, or we can solve it with Ditran. Today's presentation, we're going to focus on implicit nonlinear analysis, solution 400. And for day in, day out, the structural nonlinear problems, implicit will cover pretty much most of the problems you'll run into, unless you really get into the short duration impact type of problem. Let's take some time now. Before we look at our example, let's look into the three different types of nonlinear behaviors. We can divide nonlinear behavior into three categories. One is geometric nonlinearity, one is material nonlinearity, the third one is a boundary condition nonlinearity, and typically that will be a contact. So we call that contact nonlinearity. Let's look at, first of all, geometric nonlinearity. The term itself implies, right, it's something that's moving and deforming, so it's changing its geometry, the way it looks. And the most common type of geometric nonlinearity is large displacement, something that's deforming quite a bit in translation and or rotations. I think I'll give you, let's look at a simple cantilever beam example. That's a good example to demonstrate small displacement versus a large displacement. So I'm going to take a long and slender elastic beam, very small cross section, so I can push on it quite a bit. It's going to bend and it's going to deform and still remain elastic. Now, if we stay with our small displacement formulation, we're going to assume that the displacement is quite small. So the beam only carries shear and bending moment. And so we can make the assumption that our free body diagram and equilibrium equations are written in the undeformed position. So if we simulate this in Nastran, in the linear analysis, with this assumption, and now if I push on it more and more, you can see now here's the animated actual results. It's not quite plausible. You look at that result, the beam doesn't bend like that. Well, that's because we're pushing the small displacement formulation too far. Now, on the right-hand side, let's see. Now we're going to turn on large displacement or the geometric nonlinear capability. And now we're going to actually track the deformation step by step, incrementally solve it. And now you can see the deformation is a lot more reasonable, right? It needs to bend. And actually, when it bends more, at some point, if you look at the free body diagram, the beam will start to react tensile load inside the beam in order to react the vertical applied load. So on the left-hand side, you can see our load deflection curve, load versus displacement. For small displacement, it's constant, just a single stiffness value. For large displacement, you'll notice, though, if I start loading the beam, right, initially it's bending, but eventually more and more the load is carried by tensile load inside the beam. So it's actually getting stiffer. Deflection is getting smaller. So this is one type of geometric nonlinearity, typically called geometric stiffening because it gets stiffer. You will run into other situations when you start to load it, it will actually get softer. So you could also get geometric softening. Another common example in geometric nonlinearity is buckling. And let's look at an animation here. This is a very deep beam. So the applied vertical shear is carried by the shear web, and you can see the shear web is buckling. We can certainly do this with a linear analysis or even a hand calculation. I can calculate the initial shear buckling of 1 bay. But once you go beyond that point, you can see the buckles will start from 1 bay and they start to propagate, and eventually all the bays buckle in shear. At that point, the load will continually be carried by the panel, but now the load path changes into semi-diagonal tension. So this is an example where the deformation is changing. At the same time, the load path internally is changing. So we do have to capture this with geometric nonlinearity. Another example would be this column right here. Again, you can see as I start to push on that, the flanges will buckle first. Again, you can get a closed form solution. I can calculate the linear solution. But after the flanges buckle, the load will continue to be carried more by the joints. And eventually, you'll see the web will actually buckle also. Then the whole section goes into plasticity and the whole section cripples. So that's, again, a very good example of post-buckling, where we do have to really follow the deformation and the change of load path in our nonlinear analysis. Just one more example of geometric nonlinearity is follower force. For example, you have a pressure vessel. When you load it up, the pressure follows the deformation. Or in this example of a single force at the tip of the beam, the force, if it follows the tip deformation, then it's called a follower force. So these are examples of geometric nonlinearity. Next, let's look at material nonlinearity. I think for most of you, the most common example you're familiar with is a stress-strain curve. What I'm showing here is a stress-strain curve from a MMPDS, Mill Handbook 5, and just defining some of the terms. So this looks like it doesn't have a definite knee, so it's probably aluminum or titanium. So you can see when we make a linear assumption, we can go to this curve and say, let me go to 0.2% offset, draw a parallel line, and call that the yield stress. So if I'm below the yield stress, I have a positive margin of safety. In nonlinear analysis, there are cases, for example, at ultimate load, some cases we allow plasticity in the structure. And other examples would be when you run a fail-safe analysis and you're going to say, something has failed, but I just want to make sure this structure survives. So in that case, we want to really follow the entire stress-strain behavior of this curve. So we'll define an elastic plastic material and enter the entire stress-strain curve into the program. Another common example of material nonlinearity is rubber. Rubber or elastomers, we call them hyperelastic material. They have a very, very large strain capability. Right? For example, if you look at the stress-strain curve for rubber, you can go out to several 100%, and it stays elastic. So that's another different type of material nonlinearity. Another one, how about composites? When we perform composites analysis, you can certainly write a margin of safety on the first ply failure using any of these failure criteria. But what if you want to do a composite laminate, and I will go ahead and load the structure beyond the first ply failure. I want the ply to then progressively fail through the different plies and ultimately figuring out what the final capacity is of my laminate. We can do that by using progressive ply failure. So on the right-hand side here, you can see I have a open hole tension coupon of a composite laminate. This one has 8 plies, quasi-isotropic, and we're using the puck failure criterion. On the left-hand side, you can see the animation. That's showing the 0-degree ply. It's showing where it turns red. That means the failure index has reached 1. So you can see this 0-degree ply will progressively fail, and the load is redistributed to the neighboring elements and also to the neighboring plies. Okay, another type of material nonlinearity would be fracture mechanics. If you want to simulate a crack, growing, or in this case, delamination in a laminate or bonded joint, there are two techniques. One is VCCT, virtual crack closure technique. And in this example here, you can see I have a bonded skin to stringer joint. And I placed an initial flaw in the joint. And now as I load it, the VCCT allows me to simulate a crack propagating through the bound line. Another technique is called cohesive zone modeling. Instead of simulating the crack propagating, I actually simulate the material representing the bound line. And that material itself has a damage behavior I can present to the program. So the material then will fail progressively in simulating a crack propagating through the system. Okay, now the third type of nonlinearity is contact. We see a lot of our users coming into nonlinear analysis. First problem they run is contact. It just is very common in assemblies. This is a simple example I'm animating here. It's very exaggerated, the deformation, but this is actually a close fit lug, pin, and clevis assembly. So the deformation is actually really small. But you can see here the only load path is contact. There's nothing else. So we have to simulate contact between these contact bodies. This example on the right shows a deployment mechanism. So I have a track going through a set of rollers and guides. And this time now you can see there's contact, but there's a lot of displacement going on. All right, so this would be a large displacement analysis with contact. How about a very typical tension joint, right? This is a primary joint, two bathtub fittings that's preloaded together with a bolt. In this case, we will actually apply a preload. I'm showing here, split the bolt, apply the preload, and clamp the structure together. And then we want to see when I apply the external load, does the joint gap? So again, I need to have the two bathtub fittings and the bolt as three separate contact bodies. And now I can simulate contact between the parts. You can certainly simulate contact between shell elements, shell bodies, face-to-face, edge-to-edge, and so on. And we get people asking us, you know, one example, someone wants to simulate a cargo net capturing a UAV returning home. We can certainly do that. So this is a simple example showing you the beam elements are used to simulate the net, and it's capturing an object with the beams contacting each other and the beam contacting the solid. Okay, have a brief overview before we jump into our example problem. So solution 400, what we've shown you so far is it is a solution that we spent the last 10 years developing. And we think our solution 400 is battle tested and battle hardened because we've received a lot of user support over the years. We've been improving it. But the starting point of solution 400 is we brought in our older solutions, 106 and 129, static and transient, and we brought in a lot of the new components coming in from Mark and our new features. Components like contact are brought in from Mark. New components like solid composites and cohesive contact, a lot of the new things are directly brought into solution 400. We brought heat transfer right into solution 400. And finally, it's important we brought in linear solutions because our users do want to do, many cases, preload a structure first, do a nonlinear analysis, preload the structure, and freeze it, and do a linear analysis at that point, maybe a modal analysis or frequency response. So we brought in linear solutions as well. And listed here are just the capabilities I talked about earlier. And worth mentioning is large strain. Solution 400 thinks in large strain, so it's very good at handling large strain. And we'll cover some of the other points a little bit later. So before we look at the example together, I want to give you a couple productivity tips. We talked about how to be productive in nonlinear Nastran. When we designed solution 400, we kept two key ingredients. The first ingredient is we kept the Nastran and pattern interface really familiar to the linear Nastran pattern interface. The purpose there is we want to make sure if you're an existing Nastran user, you can leverage your know-how in linear and get up to speed really quickly in nonlinear, right? As shown here, I went ahead and drew a couple of learning curves. If you belong to the linear Nastran camp, you can see, right, your knowledge going along the vertical axis doesn't take too much time along the horizontal axis. Very easy when you transition. Now, if you want to learn from scratch another code that's nonlinear, it will probably take you more time to actually get there. So I want to encourage a lot of the linear users. Actually, that's the good news for the managers too. You certainly don't want your users to spend days and weeks getting really good at nonlinear, becomes a nonlinear expert. You probably want them to become productive quickly and leverage what they know already and be able to run nonlinear analysis quickly. Another thing we've done is our users complained about a lot of the complex nonlinear settings. So we've come up with a very small set of smart settings for you to make running Nastran nonlinear a lot easier. Okay, so let's look about the familiar interface I talked about. If you like to edit text files in Nastran, for example, here's the solution 101, and here's 400. If you look at them, they're really virtually identical except some of the new entries. So text editing wise, you can change your 101 file into solution 400 very quickly. Our recommendation though is, for really convenience, use the Patran interface. The Patran interface is very easy for you to switch from a linear interface into a nonlinear. And we do recommend the new interface we created about 3-4 years ago. And this is a dedicated implicit nonlinear preference. This preference is done specifically for you to run solution 400. It's simpler. It speaks directly to the implicit nonlinear language. That's the preference we recommend. Okay, the second thing, let's look at the smart settings I talked about. But first, let's look at how we solve a nonlinear problem. When we solve a linear problem, if I did a load deflection curve, it's pretty boring, right? It's just single stiffness. So it's a straight line. Now, if you want to solve a nonlinear problem like this, the load deflection curve shown here is a curve. I cannot solve that in one shot. So in the implicit method, this is where we start to divide the load increments. We start to divide the load into increments. And within each increment, we start to iterate and converge. So let me show you. Let me divide this up into several load increments. I'll just show you the first 2 load increments. So you can see here as the first load increment, let's say I'm applying 20-25% of the load. And you can see once I apply the load, the program will go through a few iterations. These are the little angles you see here, the little peaks. With each iteration, I'm solving the problem one more time, and it's getting closer and closer. Eventually, the unbalance in the problem becomes small enough based on a convergence criterion the user specifies. So I'm ready, let's say 20% load. Now let me apply another 20% load. Again, and again, it looks at that time what the stiffness is, makes a guess, takes more iterations, eventually converges. So you can see just going through this, the user has made a number of decisions. You're deciding how many load increments to use, how many iterations do I allow, how big a convergence tolerance should I keep? Is it really tight or loosen it? So over the years, our users have told us, hey, look, this is a great solution, but wait, there's a lot of knobs and dials and switches I have to turn to get to the right solution. Then again, I emphasize the point, we don't want you to spend days and days become a nonlinear expert. We really want you to get productive much faster. So we've come up with smart settings a few years ago. So we've gone through a lot of testing, a lot of models, and we came up with 3 settings for you to start. First one is Q linear, basically very quiet. You use this when your only nonlinearity is contact, nothing else. When you set it to this, we take one single load increment. We apply the load in one shot, and we have a very tight convergence criterion, so you can converge quickly with this setting. The second setting I would recommend for general nonlinear analysis is called mildly. This mildly nonlinear setting is good for anything with geometric nonlinearity, with material nonlinearity, and contact at the same time, right? This is a good starting point for any problem you're doing. And in this problem, the default is 10 increments, and with a pretty tight convergence tolerance. This is a good starting point for running a typical nonlinear problem. When your job doesn't converge, right, you're having problems, consider going to severely. Severely now is designed for something that involves large displacement, large strain, or when your job doesn't converge. Severely will divide the loads into much smaller increments, 50 increments. And so we take more time going through the problem, and we eventually solve the problem. So these are the 3 smart settings we recommend that you use to help you become more productive. Okay, so let's look at the sample problem we selected for today. We decided not to pick anything too realistic, too complicated. We picked something really simple. This is a aluminum splice joint. So you can see the green is a strip of skin that's been split, and we have a splice plate at the top. So both the splice plate and the skin are 80 thousandths thick. And shown below is our finite element model here. So we're applying 2,000 pounds in-plane load to it. We're simulating the fasteners with beam elements, and these are, I believe, 316 Hilux. So we could have used CFAS as well, and you notice between the red mesh and the green mesh, the mesh density are different. So the nodes don't all line up. Okay, so let's go ahead, talk about what we're going to go through. I'm going to take this problem first, run a linear analysis first. And then we'll go through and identify each type of nonlinearity, potential nonlinearity in the problem, and then we'll show you how to finish setting up the solution 400 analysis, and we'll review the results. Okay, first step then, it's always a good idea to run a solution 101 linear job. Even though you're totally confident that your job is going to encounter nonlinearity, you want to push the button right away, come back and do a solution 101 first. Gives you a chance to check out your model, and also gives you a chance to have a baseline so you can easily identify possible nonlinearities. So in this problem, you can see here, we ran the job, and because it's a single shear joint, there is quite a bit of eccentricity in the joint. So I'm getting a pretty big outer plane displacement. By the way, this animation is true scale, not exaggerated. So almost 0.6 of an inch. All right. So that should raise a red flag that maybe there's large deformation going on. Also, let's look at the stress. The maximum easy stress is 170 KSI. This part is made of aluminum alloy 2024 T3. So FT wide is about 45 KSI. So definitely we're way beyond the yield strength of the material. Okay, so now that we've run our linear analysis, we made some observations, we decided, yeah, it warrants a nonlinear analysis. But first of all, let's identify what the nonlinear effects are. The first one, let's talk about geometric nonlinearity. What you're looking for in geometric nonlinearity are things that rotate and move a lot. They buckle and continue to buckle past the initial buckling, geometric stiffening, geometric softening. So let me show you a few examples. One example here is just a wing. Something like the 787 wing is so large when it deforms. If you look at the tip deflection, it's quite a distance off from in the vertical direction. So obviously, I have to do a free body diagram in the undeformed position, not in the, sorry, I have to do a free body diagram in the deformed position, right? I cannot do that in the undeformed position. So that's large displacement. And also you notice the skin bases are buckling. They're buckling progressively one after another. So post-buckling is happening in this problem. Another example is our joint example. You can see already we show you there was quite a bit of outer plane deflection. So be on the lookout for large outer plane deflection. A typical rule of thumb, a lot of people have different rules of thumb. The one I'm used to is if your outer plane deflection exceeds T/2, or thickness divided by 2, then you should start considering large displacement effect. In our example, our plate thickness is 80,000. So once you see a outer plane deflection beyond 40,000, you might want to start looking into geometric nonlinear analysis. Another example would be unstiffened pressure vessels, like in this example. Fuel tanks, pressure vessels, when it's pressurized, the skin will tend to balloon out or pillow out. It's called pillowing. And that is a typical example of geometric stiffening. So you definitely want to turn on the geometric nonlinear capability to capture the nonlinear behavior here. Okay, so based on our linear run, we made a decision, yes, there is geometric nonlinearity. 5.58 is definitely a lot larger than T over 2. So we do need to activate our large displacement. So we'll do that in a minute. Let's hold off and let's continue with our second check, material nonlinearity. So in this example, we realize 170 KSI tells me I'm going to write a negative margin of safety on the yield strength of 45. But I'm told I'm going to run this is actually applied load as an ultimate load. I'm allowed to have some yielding as long as I don't fail the part. So I'm going to actually investigate the material into yield. So in this case, then, I'm going to enter a stress strain curve into Nastran. Nastran solution 400 thinks in large strain because it needs to handle very large strain. So we want you to enter true stress versus true strain in this case. Many of you will actually get stress strain data from engineering handbooks. They come as engineering stress and strain. So you want to make sure we have a couple of equations down here to convert your engineering stress and strain into true stress and true strain before entering them into Nastran solution 400. And then the rest is straightforward, right? Go into Patran, there's a tabular field. Just enter the results into the table, or if you want, put it in a spreadsheet and just import it into Patran. And then I can just create a elastoplastic material by using the strain curve, stress strain curve you have created. Okay, so material plasticity is actually fairly easy to model in solution 400. The third type, let's look for contact. If I animate the structure, I notice it looks like the parts are actually penetrating each other. And this effect is actually a lot more pronounced when we have users when they run a outer plane loading. For example, instead of in-plane loading here, if I apply the pressure loading to this joint will really deflect out, and you're going to see a lot more parts penetrating between the fasteners. So that's an indication to you that you need to add contact. So look for parts bumping into each other, and that will require contact. And in Nastran solution 400, we define contact by using contact bodies. So you can see here I have the example here. I will go to Patran and create a deformable body first for the strap. I can point to the property or just pick up the elements. And then I can create a second body for the skin. Again, picking up the property or picking up the elements. And then all I have to do is define a contact pair. So in Nastran, you don't have to explicitly specify where these bodies will contact. All you do is specify the bodies and that they're in a contact pair. Nastran will go through based on proximity, detect the parts, and figure out how they should interact. Okay, so now we've defined all three types of nonlinearity. Let's go ahead and finish up setting up solution 400. Like I mentioned, you definitely want to take advantage of the new preference we've set up. In the past, you can come into here, into Nastran, and you can select a structural preference. We recommend you use this new interface, Implicit Nonlinear, which is a lot easier to use for solution 400. Okay, now a couple of important parameters we need to define. First one, remember earlier we decided we do need to turn on geometric nonlinear parameter. Well, this is where you would turn it on. When you come to Patran in here, in solution 400 by default, we've turned it on for you. So come here and make sure you see large displacement and follow the load. Right? This tells me now the analysis will run through being able to handle geometric nonlinear effects. You can certainly deactivate them, right? If you want to, for example, I want to make sure I make a run and see if it matches my linear results. You can certainly come in here and set large displacement to small displacement. So it's pretty flexible. The second thing is the smart settings we talked about earlier. Come into load increment parameters, and you can see here we're offering the 3 smart defaults for you. Again, we recommend just go straight to mildly as your first try and run the job as a starting point. Okay, one last thing would be setting up the load cases. You can see here on the right-hand side, in our example here, I have one single in-plane load of 2,000 pounds. That's not very exciting, so that's just one subcase. But often in nonlinear analysis, we have multiple steps, like a bolted joint. I need to preload the joint and followed by applying the external load. So solution 400 here allows you to very easily set up multiple subcases, and within each subcase, there are steps. The subcases in solution 400 are independent. Within the subcase, the steps are dependent and are chained. So in our first example here, subcase 1 has 3 steps that are chained to each other. The end of step 1 will feed into the starting of step 2, and step 2 will feed into step 3. Okay. If you look down here, there's another example, subcase 2. I apply a preload first, and then I can do a normal modes analysis with a stretcher under a preload. There's another case where people just want to run multiple subcases. They're all nonlinear, and they're independent. And solution 400 is designed to do that. You can see here, subcase 1, 2, 3, 4 are totally independent. They can be static, they can be dynamic, they can be different disciplines, but you can run them separately, independently. Okay, so once I've set this up with my subcases and steps, we're ready to run the job. When we run the analysis, you definitely want to locate a file with an extension .sts. That's the status file. Gives you something to look at while the job is running. But you can see here, I opened this up in TextPad. You can see telling you within each increment how many cycles, right? How many iterations the job is going through. And also you can monitor how well your job is going on the right-hand side by looking at the maximum displacement, right? You can see here, if something runs away from you, suddenly you get a very large displacement. This will be where you catch it. You can also open up in real time the .fo6 file. FO6 will give you a lot more detailed description of what's going on, right? We mentioned about the smart defaults. They have preset convergence criterion set for you. Over here, you can see when the iterations are going, how well the program is doing under displacement, load, and work. Okay, and now let's say our job is finished. Let's look at the results of this solution 400 job. Remember, we've included large displacement, material plasticity, and contact. So first thing, I plot the displacement here, 79 thousandths of an inch. Okay, and you can also reference the table at the lower left-hand corner. So you can see, coming from linear to a nonlinear analysis, my displacement reduced tremendously, and now it's a lot more plausible. This is how a real structure should behave. So about 80 thousandths of deflection. Now let's look at contact. There is certainly contact, so I'm just plotting some of the contact vectors. In this problem, there wasn't that much contact force. I think the largest contact force is about 20, 30 pounds, right? Because we're not applying a load out of plane. We're really applying a load in plane. But contact is still actually important because we are picking up contact forces here. How about stress? Well, when I ran the analysis with a full stress strain curve, I'm coming up with 4950, 50 KSI, right? That's a lot lower than the 170 KSI we saw earlier, right? Right now, it faithfully followed the stress strain curve I entered and told me that the maximum plastic strain is not too much. It's about 0.4 of 1%. All right. Now, by the way, this problem, if I had kept on pushing it, because we've turned on the large strain capability in solution 400. There's no problem to keep on pushing this problem, and my plastic strain can go into 1%, 2%, 10%, and so on. Okay, and finally, we mentioned the displacement here is 79,000. Remember, our thickness was 80,000, so this is still pretty close to the actual thickness, so it's significant. If we look at the low deflection curve here, you notice that the blue curve is the linear run, and the nonlinear run is the red. You notice it's curving up because as we load the structure, as it deforms, right, the load path is changing. So it is stiffening, so the red curve curves upward. So geometric nonlinear effect is actually present and is reflected by the low deflection curve here. Okay, so let's summarize what we went through today. Right, I show you a couple of important things about using solution 400 productively. Number one, definitely want to leverage your linear Nastran know-how. Now, use the Patra interface if possible. Will really speed things up for you to get up to speed quickly into nonlinear 400. And second thing, start out your settings by using one of the smart settings. Also, just a quick review of what we went through in the example. Run a linear analysis first. Check out the model, understand possible nonlinear effects. Then go through them individually and define them, add them to the solution 400. And finally, when you set up the job, remember to go in there and check the smart setting. That's where you set this up, and set up your subcases and steps. Finally, review your results. And so that takes us to the end of our presentation today. Thank you for watching the webinar.
Thank you, everybody, for attending this webinar. Thank you, Hanson, for your informative presentation. And, at this point, I'm going to end the presentation. Hope to see you all in future webinars. Thank you and have a good day.